Hello everyone, my name is Jie. I'm from Skyworks Solutions. Today I will talk about the electrode design of aluminum nitride Lamb wave resonators. This is a theoretical study for the research purpose. Here is the outline, the motivation, introduction to aluminum nitride Lamb wave resonators, and then 4 considerations on the electrode design, including the impact of electrode configurations, electrode materials, electrode thicknesses, and IDT duty factor. Finally, the conclusions. As we know, in the RF front-end module, the SAW and BAW filters are very important components for signal filtering at the very first stage. In spite of the drastically increasing number of bands and the complexity in the wireless communication system, the SAW and BAW filters are still discrete components packaged in individual dies, usually separated by bands, and they are also discrete from the other RFIC components. In a trend toward highly integration and co-design of the RF front-end architecture, the high-performance and CMOS-compatible microacoustic resonators is highly desirable for the future single-chip RF transceiver. And the filters is preferable to covering the frequency range of around 600 MHz to above 4 GHz. However, the current BAW and SAW filters have limitations to enable this integration. The BAW resonators' resonance frequencies are determined by the piezoelectric film thickness, making it difficult to enable multi-frequency on a single chip. And the SAW resonators can do multi-frequency but have high-frequency limitation due to the low phase velocity of the relay wave. The Lamb wave resonator combines both advantages of the BAW and SAW filters. Its resonance frequency is lithographically defined by the interdigital transducer, like SAW, so it can enable multi-frequency. And the phase velocity of the AlN Lamb mode in the aluminum nitride is large, like BAW, so easy to achieve high frequency. This figure shows the phase velocity of the AlN mode, which is close to 10,000 meters per second. And it has a weak dispersion, allowing for manufacturing tolerance. In addition, the suspended structure reduces the energy leakage and enable high Q. The free edge reflectors enable small size comparing to using grating reflectors. The piezoelectric material is the sputtered C-axis oriented aluminum nitride, which is CMOS compatible, and it can enjoy the mature fabrication experience of F-bar directly. However, unfortunately, the aluminum nitride Lamb wave resonator usually show only medium coupling coefficient. The reported results are mostly around 2%, limiting the filter bandwidth. In spite of some novel techniques to enhance the coupling coefficient, like scandium dope tilt aluminum nitride, actually at the first place, by just carefully designing the electrodes, the coupling can be boosted to a large extent. Although the eldest approach in this equation, using the open surface and metallized surface velocity, is widely used to evaluate this intrinsic coupling coefficient. It's actually a simplified model by only considering the piezo material property and the electrical excitation boundary condition. In order to take into account the actual potential field, the IDT reflection level, and the mechanical loading effect, here we use the FEM simulation to simulate the effective coupling coefficient. In the right figure, we compare 4 electrode configurations instead of the 3 configuration in the left. This is because for the IDT with the bottom electrode case, there are 2 conditions. One is the blue curve in the right, which is when the ground bottom electrode is in floating potential. And the red curve in the right figure is when the bottom electrode grounded. Taking a closer look at the 4 configurations, we see the transducers can enable vertical and lateral excitation in the piezo material. When the aluminum nitride plate is very thin, the vertical field is stronger than the lateral, and if we only look at the vertical excitation, we see the excitation strength proportional to the coupling value. Again, when the aluminum nitride plate is thick, the vertical field is stronger, and again, the coupling coefficient corresponds to the excitation level. So comparing these four configurations, we see the double IDT configuration enable largest effective coupling coefficient, and the floating bottom electrode is better than grounded bottom electrode. For single IDT configuration, aluminum nitride needs to be relatively thick to around 0.5 lambda. Although the impact of electrode metal material is probably clear for SAW resonator and F-bars, there haven't been systematic study for Lamb wave resonators. Here shows the impact of different electrode material on the phase velocity. The blue circle is when the aluminum nitride is sufficiently thick, then the loading effect is just proportional to the metal density. This is intuitive. When the aluminum nitride is very thin in the green circle, the phase velocity is just proportional to the sound velocity in that metal. Similarly, here shows the electrode material on the coupling coefficient for the single IDT configuration in this figure. Again, when the aluminum nitride is sufficiently thick in the orange circle, the coupling coefficient is enhanced and proportional to the acoustic impedance of the electrode material, because larger acoustic impedance gives larger reflection coefficient. And when the aluminum nitride is very thin, the heavier metal has stronger loading effect. This is similar case for the other three electrode configurations. So light metals are preferable to be used for bottom electrode to reduce the loading effect for thin aluminum nitride like aluminum titanium, and the large acoustic impedance metal is preferable to use for thick aluminum nitride to enhance the coupling coefficient like tungsten, platinum, moly. It's very interesting to notice that in this double IDT configuration, if large acoustic impedance material is used, the coupling can be as large as close to 7%. If we use different metals for the IDT and bottom electrodes, it's preferable to use large acoustic impedance metal as IDT to enhance the reflection, and the small density metal as bottom electrode to reduce the loading effect. The tungsten and aluminum is used as example here. Since tungsten has large acoustic impedance and aluminum has low density, we can see in the both configuration, the IDT with floating bottom electrode and the IDT with grounded bottom electrode, the green curve, which is when tungsten as IDT and aluminum as bottom electrode, generally shows largest coupling. Here, this contour plot shows the effective coupling versus IDT thickness for the single IDT configuration, and the material is platinum. The first observation is that the effective coupling reaches the maximal value at a certain point in the middle. This is because when the IDT thickness is increased, the reflection of IDT increases, which enhances the electromechanical transduction. But when the electrode becomes too thick, the non-piezo layer deviates the resonance wave from the piezo layer and reduce the piezo transduction. Again, when aluminum nitride is very thin, in the red circle, the loading effect dominates, so we prefer thinner IDT. And when aluminum nitride is sufficiently thick, the reflection dominates, and we prefer thicker IDT. All the previous results are with the duty factor of 0.5. However, similar to SAW resonators, the change on duty factor also impacts the coupling coefficient. This figure shows the effective coupling versus different IDT duty factors for different materials. We can see, again, there is a top value because of the balance between reflection and the non-piezo loading. For most metals, including tungsten, platinum, moly, titanium, the top value is when duty factor equal to 0.55. For gold and copper, the effective coupling reach maximum at 0.45 and 0.5. This is because gold and copper is relatively soft and heavy, which means they destroy the wave concentration from piezo film and destroy the wave shape more than the other metals in spite of the enhanced reflection. So to sum up, aluminum nitride is a good candidate for future highly integrated RF front-end because it has high frequency and multi-frequency ability comparing to ball and saw and is CMOS compatible. Aluminum nitride has small size, high phase velocity, large Q manufacturing tolerance, but its coupling coefficient needs improvement. This can be done by carefully designing electrode. For electrode configurations, double IDT enable largest coupling, floating bottom electrode better than grounded ones. Single IDT needs relatively thick aluminum nitride. For electrode materials, large acoustic impedance used as IDTs can enhance the coupling, especially when aluminum nitride is thick, and large density metal will lose the coupling, especially when aluminum nitride is very thin. For electrode thickness, there is a top value because of the balance between reflection and the piezo dead loading effect. For IDT duty factor, for most metals, the coupling reaches a maximum at duty factor of 0.55, but for soft and heavy gold and copper, the coupling peaks at the lower duty factor. Thank you for your time. Question?